Welcome viewers. In this video, we are going to solve GATE Mechanical 2023 papers and the problems which are associated to applied mechanics and design, that is engineering mechanics, mechanics of materials, theory of machines, vibration and design of machine elements. So let us start. The effective stiffness of a cantilever beam of length L, flexural rigidity EI, subjected to transverse steep load W. So what is stiffness? We know that stiffness is W by delta. Delta is the deflection at the point where load is applied. So what is delta? We know that delta is WL cube by 3EI. 3EI. So W by delta, that is K, which is equal to what? W by delta is 3EI by L cube. 3EI by L cube. So this is the answer to the problem and option A is the correct one. Now let us move to the next problem. The option shows frames consisting of rigid bars connected by pin joints. So these are the pin joints. Okay. Which one of the frame is non-rigid? Non-rigid means degree of freedom is 1, at least 1. Degree of freedom is 1. When degrees of freedom is 0, that is degrees of freedom is 0, that is rigid, that is a structure. Degrees of freedom is negative means statically indeterminate, and this is called mechanism or non-rigid. So this is obviously 4 bars are there and 4 revolute pairs or pin joints. This is a structure or rigid. This is rigid. This is also 3 members loop. This is also a rigid. This is also a truss structure. You can see this extra member is there. So this is also rigid. But here, if you consider this loop, this is a 4R mechanism. This loop is a 4R mechanism. So due to this loop, this becomes non-rigid. Okay, we have done this in truss classes. Now let us move to the next problem. The SN diagram or SN curve from a fatigue test of steel is shown. This is S, this is L. Which one of the option gives endurance limit? Endurance limit means the corresponding stress value from which the line becomes flat. That is, if I increase the number of cycle, the load will not change. So asymptotic, this curve becomes asymptotic at 4, that is N4 cycle, and corresponding stress value is what? Corresponding stress value is S4. So SE is S4 here. So which option is correct? That is D is correct. D gives S4. Now let us move to the next problem. A beam is undergoing pure bending. So this is the beam which is going on pure bending. The stress strain curve for material is also given. That is, up to this it is elastic, after that perfectly plastic. Plastic. So if this is the yield limit, after that is corresponding yield strain is this, corresponding yield strain. After that, if we increase the strain, what happens? The stress value doesn't change. Stress value is constant. Okay. So this is elastic, then perfectly plastic. The yield stress of the material sigma y, which is given. Which of the options given represents bending stress distribution at cross section AA, this cross section, after plastic yielding? Okay, after plastic yielding. Now this is stress Stress varies. So this is the neutral axis here. Corresponding neutral axis is this one. This is neutral axis of the beam. And this is the neutral axis of the cross section. About this, the stress varies linearly. That is, this is within this region. This is elastic region. So this is elastic part of stress distribution. That is, the beam is under elastic region. Okay. B is also under elastic region because it goes linearly vary. Now, when it has been asked to distribution, bending stress distribution at cross section A after plastic yielding, that is after this point. After this point, what happens? If I increase the strain, you can see, if I increase strain up to this value, then also the stress remains sigma y. And you can see that that is entire layer at neutral axis also, the neutral axis also goes under plastic yielding. So this is one stress distribution. This is correct one. This may happen. Okay. So what is asked this question? You can, which of the options represents bending stress distribution at cross section AA after plastic yielding? Here also you can say at the edges, that is at this edge, that is farthest from the neutral axis, the stress value goes to yield stress. That is, strain there is somewhere, that is up to this part, up to this and this, the strain goes beyond the yield stress. That is up to this. Let me erase this and explain. Say here, for these two layers, this and this, strain value goes beyond this epsilon y, somewhere here. But this zone and this zone is under elastic. That's why what happens? That's why which is under elastic, that is linear distribution. After that it becomes constants. So here this zone is under plastic yielding, and inside this layer, that is in elastic. So this is plastic, these two, and inside this is elastic. And this for this whole layer is under plastic. So both this C and D option gives the stress distribution at cross section after plastic yielding. Here entire region, entire section under plastic yielding. Here only this somewhere layer, extreme layers are plastic yielding and inside is elastic. So these two options are correct here. Now let us move to the next problem. The principal stresses at point P in a solid are, say, sigma 1 is 70 MPa, sigma 2 is minus 70 MPa, and sigma 3 is 0. Principal stresses. The yield stress of the material, that is SYT, or yield stress in tension, is 100 MPa, which is given. Which predictions about material failure at point P, this is the stress of stress at point P, is or are correct? Let us check option A. Maximum normal stress theory predicts that material fails. What is maximum normal stress? Sigma max is nothing but sigma 1, that is 70 MPa. And that is sigma max here is less than SYT. So this doesn't fail. So this is incorrect. Maximum shear stress theory predicts that materials fails. What is the maximum shear stress theory for this state of stress? Tau max. Tau max is what? Tau max is what is tau max? That let me draw the Mohr circle. Sigma n and tau. So if I choose this, uh, sigma 1, yes, sigma 1, here, sigma 2. So tau max here, that is the radius of the Morse circle is nothing but that is also 70 MPa. That is tau max is nothing but tau 1, 2, between 1 and 2. And 1 and 3 is like this, and Morse circle between 2 and 3 like this. So this will be maximum. Let me neglect this 2. So this is maximum value is 70 MPa. Now, according to maximum shear stress theory, what is SY? That is yield stress in shear. That is 0.5 SYT. SYT is 100. So this is 50 MPa. So tau max is more than SY. So it will fails. So according to maximum shear stress theory, the material will fail. This is correct. Maximum normal stress theory predicts. Now let us check C. Sorry. Let us check C. Maximum normal stress theory predicts that material doesn't fail. This is also correct because we have seen that it will not fail. Correct. Maximum shear stress theory predicts that the material doesn't fail. That is incorrect. According to maximum shear stress theory, it fails, but according to normal stress theory, it doesn't fail. Okay, so we have solved this. So B and C are correct. This is a multiple option questions. Let us move to the next problem.
Are you a GATE mechanical aspirant? Then you are at the right place. Join Mechanical Academy, your ultimate gateway to IITs and PSUs. Meet with our expert faculties. Their details are shared here. Both of them having more than 10 years of teaching experience for GATE. We provide video lectures, live classes, solution of previous GATE 20 years papers, study materials in well-documented book form, doubt solving, and last but not the least, test series. Your dreams course starts here at Mechanical Academy. For details, WhatsApp 8777035176. Please follow our YouTube channel and books. Links are provided at the description box. So, looking forward to meet you soon.
Which plot shown is or are? That is, there may be one option or two option. Valid Morse circle represents of plane stress in a material. The center of each circle indicated by O. So here this may be a Morse circle for plane stress. This is for pure shear. This is Morse circle for pure shear. This may not happen because this is the axis. It may not go. The center may not go beyond the axis. Here, this also the center lies on the normal stress axis. This is also possible. Whereas this never happens. So M1 and M2 are possibles. So option A and C are correct. So both the options are correct. Now let us move to the next problem. Two meshing spar gears 1 and 2. This is 1, this is 2. Diametral pitch of 8 teeth per mm. So module is what? 1 by diametral pitch. That is this much mm. Module is 1 by 8 mm. Module is inverse of the diametral pitch. So if diametral pitch is 8 teeth per mm, so module is 8 mm. Angular velocity ratio omega 2 by omega 1, mod of that, because do not consider the sign, 1 by 4. Okay, have their centers 30 millimeter apart. So this is 30 millimeter. That is RP1. This is RP1 and this is RP2. Pitch circle radius RP1 and RP2 is 30. That is DP1 and DP2 is pitch circle diameter is what? Say module into N1 plus N2. N1 and N2 are number of teeth. So this becomes diametral piece. So that should be 30 into 2. Radius into 2 is the diameter. So N1 plus N2 is what? 60. M is 1 by 8. So 60 into 8. M is 1 by 8. So 60 into 8. So N1 plus N2 is 480. Now, from this we can find, that is, the speed ratio is given, that is N1 by N2 is 1 by 4. That is N2 is 4 N1. Now let us put on this equation. If N2 is 4 N1, that is 5 N1 is 480. That is N1 is 480 by 5. 480 by 5 is 96. So it has been asked to find the number of teeth on driver gear 1. That is N1 is 96. So this is the answer to the problem. Now let us move to the next problem. The figure shows a block mass M, 20 kg. M is 20 kg. Attached to a pair of identical linear springs where stiffness are K. K is 1000 Newton per meter. The block oscillates on frictionless horizontal surface, that is this surface. Assuming free vibrations, the time taken by block to complete 10 oscillations. Okay, so from this the springs are in parallel, so omega n will be what? Effective stiffness is 2k, that is 2k by m, 2k by m, that is omega n. Okay, that is omega n. What is frequency then? Frequency is, this is omega n is radian per second. Radian per second. Now, what is time cycle? Time cycle for one oscillation. Now, one oscillation means, one complete oscillation means 2 pi rotation. 2 pi rotation. That is, if frequency is this much radian per second, then time should be what? What should be the time? That is 2 pi by omega n second for one cycle. For 10 cycles to complete 10 oscillations, what is the time? Time is 10t. That is 10 into 2 pi into omega n. Omega n is 2 into k is 1000 and m is 20 kg. 20. That is 10 into 2 pi divided by 2 cancel, root over 100 is 10. So time is 2 pi second. 2 pi is 3.18, that is 3.14, 6.28 second. So the answer is 6.28. Now let us move to the next problem. The braking system shown in figure uses a belt to slow down a pulley rotating in clockwise direction by application of force P. So this is the braking force P. This is the pulley which is rotating in clockwise direction. The belt wraps around the pulley over an angle, that is wrap angle alpha is given 270 degree, that is 3 pi by 2 radian. The coefficient of friction between the belt and pulley mu is 0.3. The influence of centrifugal force on the belt is negligible. So if such that, and if I draw the free body diagram of the pulley only, say this is the free body diagram of the pulley which is rotating in clockwise direction, this direction, and this tension is T2 and this tension is T1, which is mentioned here. Now it is rotating along T2. So T1 will be greater than T2 and ratio of T1 by T2 will be e to the power mu alpha. Okay, as centrifugal forces negligible, so we can use this equation. We can use this equation. Now from this we can easily find the value of T1 by T2. That is e to the power mu is 0.3 into 3 by 2. So calculating this, you will get 4.113. During braking, the ratio of tensions T1 by T1 to T2. So this we have already got. The belt is equal to, that is, this ratio has to be determined. This is very simple problem. That answer is 4.113. So this is the answer to the problem. It has been asked to round up 2 decimal places, so you can write 4.1. Now let us move to the next problem. A spherical ball, this is the spherical ball, weighing 2 kg given, dropped from height 4.9 meter given onto a immovable rigid block. This is the rigid block. This is the rigid block. Okay, let me erase. Now, as shown in the figure, if oscillation is perfectly elastic, what is momentum vector of the ball just after impact? Take acceleration due to gravity, value of g is given and option has to be selected. Now this is it will come through this path. The ball will come through this path. Now what will be the velocity? Just before impact, what is the velocity? That is the potential energy will be converted to, potential energy of the ball will be converted to kinetic energy. That is applying the principle of conservation of energy, we get this. That is m cancelled, v is root over 2gh. That is 2 into 9.8, it is given, and h is 4.9, and that is 9.8 meter per second. 9.8 meter per second. Now this is 30 degree. So if I draw a perpendicular on the on this inclined surface, this will be this is the normal to the inclined surface. Okay, now as this is a perfectly collision, then this angle, what should be the this angle? If this is 30, then this angle is also 30 degree. This angle is also 30 degree, and it will now the it will move through this. After collision, it will move through this, that is, this angle is also 30 degree. So this is the final direction of the spherical ball. Now what is momentum just before collision? That is, momentum is m into v. That is, m is 2 into 9.8, 2 into 9.8. Okay, that is 19.6, 19.6 kg meter per second. Okay, now this is the vector. This is the vector after collision. Momentum will be, this momentum is also 19.6 kg meter per second. Now if I break it into I and j direction, what is I? I is along x, j is along y. So this is I and this is j. So if this angle is 30 degree and this is 30, then this is also 30 degree. Okay, this angle is also 30 degree. So the final momentum, what is has been asked, what is the momentum vector of the ball just after impact? So that momentum will be what? That is, momentum after impact is 19.6 along I the angle is 30 degree. So cos of 30 degree I plus. So let me write down in the next page because the space is limited here. 19.6 cosine 30 degree I plus 19.6 sine 30 degree J. And if we calculate cos 30 into 19.6, that becomes 17 I plus 9.8 J. So which option is correct? That is, we can see that option C is the correct. So this is the correct answer. Now let us move to the next problem. Now let us solve this problem. The figure shows a wheel rolling without slipping on horizontal plane. This is the horizontal plane and this is the wheel with angular velocity omega 1. A rigid bar PQ, this is P, this is Q, pinned to the wheel at point P. So here the bar is pinned to the wheel and end Q slides on the floor. That is, end Q slides on the floor. What is angular velocity omega 2 of the bar PQ? This is omega 2. So we have to find the value of omega 2. For this problem, we shall use instantaneous center of velocity. Okay, this will be very easier for this problem to solve this. This is very easy problem. We have done this several times in our full course. Now let us see. First, the fixed link is 1, that is the horizontal floor. This is 2 and the bar is 3. So there are 3 rigid bodies. So how many relative instantaneous center will be there? 3C2, that is 3, and we know that I12, I13 and I23. Now let us locate the points. 2, 2 having 2 rolls without slipping on 1. That is, the instantaneous center lies at the point of contact R. That is I12. Where is 2, 3? So this has been located. Now 2 and 3 are connected by a hinge joint here, hinge or revolute pair. So 2, 3 lies here because this point will move together. At this point 2 and 3 will have same velocity. Located. Now Q slides as well as rolls on 1. So I13 will lie at a at the at any point on the common normal. So if I draw the common normal between 3 and 1, 3 and 1, this is the common normal. So I13 lies anywhere on the common normal, that we do not know. So this is one condition, that I13 lies on this line, that is the common normal. And another condition, according to Arnold-Kennedy's theorem, we know that these 3 relative instantaneous centers are collinear. So if I join these 2 and extend this, that will meet this line, that will be nothing but the location of I13. There is not enough space and bending this line, this should be straight line. So this is I13. So 3 instantaneous centers we have located. Okay. So 3 instantaneous centers we have located. Now the question is, now we know that 2, 3 is the relative instantaneous center for body 2 and 3. So at 2, 3, that is at point P, both body 2 and 3 will have same velocity. That is, velocity of body 2 at point P is equal to velocity of body 3 at point P. What is velocity of body 2 at point P? Velocity of body 2. Body 2 has a rotates with angular velocity omega 1. So the velocity will be along this direction, and that should be omega 1 into rp, omega 1 into rp, because this is the instantaneous center. So body 2 has a pure rotation about r, and that should be equal to what? That should be equal to velocity of body 3 at point P. That is what. Now, what is I13? What is I13? One is fixed. One is fixed. So, relative instantaneous center about a fixed leg, that nothing but the absolute instantaneous center of the body 3. That is absolute instantaneous center of absolute IC of body 3. Relative instantaneous center about a fixed body is nothing but absolute instantaneous center, okay, of body 3. So what should be velocity of body 3 at point P? That is, we can consider that body 3 has a pure rotation about this point I13. Okay, so say I13, this point we have denoted PQR, and that is S. This point is S. So omega 2 into SP. S. Okay. Now omega 2 is RP by SP into omega 1. Omega 2 is RP by SP into omega 1. That is this ratio of RP. This is RP and this is SP. RP and SP. Now let me draw it here. There is limited space. Okay. This point is S. This is P. This is R. This is R. Okay. Now let this point is U and this point is T. Now let us consider triangle PRT. This triangle and triangle. I am drawing this with green color. This triangle PSU. They are similar triangle because this is 90 degree. This is 90 degree. This angle and this angle are same. Okay. And this angle and this angle are same. So they are similar triangle. That is RP by SP. RP by SP is what? Ratio of RP by SP is the ratio of RT and here PU. RT is what? This is 2 meter. It is given. This is 2 meter. So 2. And what is P into U? P into U is nothing but this. This is 8 meter. It is given 8. So 1 by 4. That is 0.25. So RP by SP, this ratio we have determined. This was needed. RP by SP, that is 0.25 mega. Okay, so we have solved this easily. So which option is correct? Here option D is the correct one. Now let us move to the next problem. Here a beam of length L, this is the length L, loaded in XY plane, this is X, this is Y, by uniformly distributed load, that is Q obviously, and by a concentrated tip load to Z axis, this is Z axis, as shown in the figure. The resulting bending moment distribution about Y and Z axis denoted by My and Mz. Which of the options given depicts correct, qualitatively correct variation of My and Mz? So first let us check for this distributed load Q. Now this distributed load is on which plane? Is on XY plane. This is on XY plane. That is, the moment created will be along which axis? That is, this is the moment. This is the moment which will be created along Z axis. Which will be created along Z axis. This moment is about Z axis. So Mz, variation of Mz, this is a uniformly distributed load, we know that distribution will be that will be negative at the fixed end and parabolically distributed like this. So MZ distribution is like this. Now let us check. Second option is the MZ. This is not correct. This is not positive bending moment, so this is incorrect. This is obviously incorrect because that will be maximum at the fixed end. So this option is the correct one. So only MZ is correct, so we do not check this. Now this is a P load, and the bending moment will be maximum at the fixed end and zero. So this option is the correct one. Okay, so by checking this one only, we got the answer. That is option B is the correct one. So we have solved this. Now let us move to the next problem. The figure shows a thin-walled open-top cylindrical vessel, radius r and wall thickness. So radius is r, thickness is t. The vessel held along brim, this is the brim, contains a constant density liquid to height h. This is the height h. Constant density liquid. Say liquid is density is rho. Neglect atmospheric pressure, that is P atmospheric is 0 here. The weight of the vessel and bending stress in the vessel walls. Okay, so neglect atmospheric pressure as well as weight of the vessel and bending stress in the vessel wall. Which one of the plots depicts qualitatively correct depending of the magnitude of axial wall stress? Axial stress is sigma 1, that is along this direction. Say along this direction sigma 1, and circumferential wall stress sigma 2. Which variations are correct? Now if I consider any point, say any point here, the distance is say y along this direction. So what will be sigma 2? Sigma 2 is always PR by T. Now what will be pressure here? Pressure is what? Rho Gy into R by T. That is, y is 0 at this point. At the surface y is 0 and maximum is h at the y equal to h. So it will linearly vary. Sigma 2 will be linearly vary. That is, if I here there are stress versus y plot. So as y increases, sigma 2 will be increases, and sigma 2 is 0 at y equal to 0 and sigma 2 equal to rho g h r by t at y equal to h. That is the maximum value. So that is linearly varying. So this option is giving the correct sigma 2, correct sigma 2. This may be also, this is also correct, but here sigma 2 is constant, which is incorrect. So these three may be correct. Now let us check about sigma 1. Now what is about sigma 1? At any section, that is at any section, say here, here, every y. If we take a section, say here, 3 sections, say here, here, and here, 1, 2, 3. In any sections, what about the sigma y? That is, if I draw the 3D view, if this is the vessel, say at any section 2, that these are the sigma 1, and that will always balance the weight. That is sigma 1 into 2 pi RT is the weight of the liquid, and that is the weight. So this sigma 1 will balance the weight. So if I take any section anywhere, the value of sigma 1 is always W by 2 pi RT. That doesn't varies on the pressure. Okay, so sigma 1 is constant. Now here or we can see that sigma 1 is constant. So this is both are correct. Sigma 1 and sigma 2 variation correct. Whereas Here sigma 1 is varying, so incorrect. Here sigma 1 is varying, so this is incorrect. So option A is the correct for this question. Now let us move to the next problem. Cylindrical bars P and Q, this is P and this is Q, have identical lengths, both having same length, say L, and radius. That is, both having, if radius are same, then both having same cross sectional area, say A, but are composed of different linear elastic materials. P and Q are of different linear elastic materials. The Young's modulus and coefficient of thermal expansion of Q are twice the corresponding value of P. That is, EQ is twice of EP, Young modulus, and alpha Q is twice of alpha P. Assume the bars to be perfectly bonded at interface. So these are two interfaces perfectly bonded. And weights to be negligible. Bars have negligible weights. The bars are held between rigid supports. These are two rigid supports. So rigid supports do not allow to elongate the bars, as shown in the figure, and the temperature is raised by delta T. So temperature is raised by delta T here. Assume that the stress in each bar is homogeneous and uniaxial. So stresses are only along uniaxial stress, that is longitudinal stress. And bar are homogeneous, that is cross-sectional area of the bar at each point is same. And denote the magnitude of stress P and Q by sigma 1 and sigma 2. So stress on bar P is sigma 1 and bar Q is sigma 2, respectively. Which of the statements given is or are correct? So first statement, the interface between P and Q moves to the left after heating. So this is the interface. So interface moves which direction? First of all, we have to calculate. And option B gives interface between P and Q moves to the right. Which one is correct, we have to determine. This is one aspect. Another aspect, that is stress of P and Q. Two options are given, that is sigma 1 is less than sigma 2 or sigma 1 equal to sigma 2. So first of all, let us come to the figure. This is the figure, and given parameter is that EQ is twice of EP and alpha Q is also twice of alpha P. Now temperature is raised by delta T, but these two are rigid supports. These two are rigid supports. So the length of the resultant length of P and Q will be unchanged. That is, the final length of P, combination of P and Q, will be also 2L if they have same length L. So, but at elevated temperature they will elongate, but these two supports do not allow them to elongate. By which? By providing compressive forces. Let us consider compressive forces at this, or already P is given, so we have to use different notation, say F, F prime and F. Now if we apply at equilibrium, if we apply the equation of statics, that is f of x equal to 0, by doing this we will get f prime equal to f. But this equation is not able to give the value of f because two unknowns, one equation. So this is a statically indeterminate problem again. So f dash is nothing but f. So from this we can only consider that both end force is F. Now if force is F, then on P what will be the stress? That is, if we draw the free body diagram of P, then force, this is the, if area is A, both having same area, then stress on P, that is sigma 1, is F by A. Similarly, if we draw the free body diagram of Q, this is F and this is also F. So sigma 2 is also F by A. So we got the first answer, that is sigma 1 must be equal to sigma 2. Sigma 1 must be equal to sigma 2. So option D is correct, 1. Now we have to calculate that the movement of the interface. This is the interface where it will goes. To get that, we have to calculate the final length of two bars respectively. Say for bar P, initial length was L. Due to temperature rise, the elongation will be L alpha P delta T, and due to this compressive stress, it will the length will be reduced by sigma L by EP. So this is the final length of bar P. So this is the final length of bar P. And what will be the final length of bar Q? Final length of bar Q will be L, that was the initial length. Elongation due to temperature rise, L alpha Q delta T, and reduction due to compressive stress, sigma L by EQ. Now the boundary condition is that what? That is, their final length will be also 2L, because these two rigid supports do not allow P and Q to elongate. So their final length will be also equal to 2L. So this 2L and these L's are cancelled. Now we can write L alpha P delta T minus sigma L EP. This is change in length of, and here L Q delta T, L alpha Q delta T minus sigma L EQ. So these two becomes 0. That is, change in length of P plus change in length of Q is 0. But here we have to calculate that this interface will move in which direction. So from change in length of P and change in length of Q, these are two expressions. Here we can easily understand that delta L P is less than delta L Q. Why? Because alpha Q is 2 alpha P. So if we replace this alpha Q by alpha P, let me replace. So here 2 alpha P and 2 EP. That is, this positive term here is more than this, and this negative term is less than compared to this negative term. So here we can say delta LP is less than delta LQ, and their summation is 0. That is, the Q will elongate, that is, delta LQ is positive and delta LP is negative. P will compressed. That means the junction will move to the left. So junction will come somewhere here. junction will move to the left. So the interface or junction between P and Q moves to the left. So this is another correct answer. So option A and D are correct here. So here it has been asked the area moment of inertia about y-axis of a linearly tapered section. This section is given as to be determined. So this is the axis. Now let us divide it into three parts. This is 1, this is 2, and this is 3. So 1 is a rectangular element and 2 and 3 are triangular element. So for a rectangular element, say this is the axis and this is the rectangular element. This is B, this is L. What should be the, say this is y axis. So what should be IY? If I take an element, distance x and thickness of the element is dx. What is the area? B dx. And what is the distance? That is x, so x square. So we have to integral over 0 to L. And doing that, b x cube by 3 limit is 0 to L, that is b L cube by 3 for the rectangular element. Now we have two triangular element, 2 and 3. Let us do it for one triangular element. Sorry. Say this is B prime, this is L. Let us take a section anywhere here at distance x and with thickness is 2x. Now what will be IY? If this is y, then IY for the triangular element, here the width will be B prime x by L, B prime x by L, that is the width, into dx is the area and distance is x, that is x square. So IY is B prime L, that should be integral 0 to L. B prime L x is cube, there should be x to the power 4 by 4 integral 0 to L. That becomes b prime L cube by 4 for one triangular element. Now here we have two triangular element. So what will be IY? Total IY is for the rectangular element BL cube by 3 plus 2 into B prime L cube by 4, that is BL cube by 3 plus B prime L cube by 2. So IY is B is what? For the rectangular element, B is what? B is 1.5 plus 1.5, 3. So 3. L is 12. Plus, here, what is B prime? For element B prime, this is also 1.5. So B prime is 1.5. L is 12. That is 12 cube. This should be 1 plus 1.5 by 2, that is 0.75. 0.75. And calculating this, we will get 3024 meter to the power 4. 3024 meter to the power 4. So the answer is 3024. Now let us move to the next problem. A cylindrical bar has length L is 5 meter. Cross-sectional area S, denoted by S, 10 meter square. The bar is made of linear elastic material, okay, with density is given 2700 kg per meter cube. Young's modulus, value of Young's modulus is also given. E is 70 GPa. Bar is suspended as shown in the figure in a state of uniaxial tension. Okay, uniaxial due to self weight. Due to self weight, the elastic strain energy stored in the bar has to be determined. Okay, and unit is joule. Round off to 2 decimal places, value of G is given. To do that, we have done this. Let us take a section anywhere here. Small element at distance x from the free end and thickness is dx. Now, at this layer, there is no load. And we know that due to axial loading, the strain energy due to axial loading is what? Integral 0 to L p square dx by 2 EA. Okay. Now on this element, what is the load at any section? That is, at this section, load of this green hatched part will be act. So that load will be what? That is, here, if load is P, that should be weight of this green hatch part. Okay. At free end it is 0, then slowly it is increasing as we go upward. So P should be, what should be the volume of this? That is S into X is the volume. S into X is the volume. Then rho is the weight. Then G. Rho is the mass. Then G. That is the total load. So let us put now here. So there should be integral 0 to L S X rho G square dx 2E A. Sorry, I'm extremely sorry because we have defined here area by S and then our actual notation area is A. So sorry, I'm considering that area is A, not S. Okay, then there may be a misconfusion. That is A. So that should be A square rho G whole square 2EA x square dx, that is x cubed by 3 integral 0 to L. That is A rho G square 2E L cubed by 3. That is, final expression is A rho G square L cube 6E. So this is the expression of strain energy stored. So U is A is, sorry, let me do it here, 10 into rho is 2700 into G is 9.8 square into L is 5 meter, so 5 cube divided by 6 into 70 into 10 to the power 9. All are in SI unit, so strain energy stored will become in joule. Now there are two zeros square, that is 40 and 10, that is 50 we can cancel, that is 27 into 9.8 square into 125 divided by 6 into 70 into 10 to the power 4, because we have cancelled 5 squares, 50. Sorry. Now let us calculate this and you will get a value 2.08 joules. So the answer is 2.08. 2.08. Now let us move to the next problem. A cylindrical transmission shaft, length is 1.5 meter, diameter is 100 mm, is made of a linear elastic material. Shear modulus G is 80 GPa. While operating at N is 500 RPM. The angle of twist across its length is found to be 0.5 degree. that is theta. Angle of twist is theta. 5 degree, that is 0.5 into pi by 180 radian. The power transmitted by the shaft is to be determined. This is very easy. That is theta equal to TL by Gj. That is torque is Gj theta by L. Let us put the values. 80 into 10 to the power 9 into pi by 32. D is 0.1. 0.1 to the power 4 into, this is the value of theta, 0.5 into pi divided by 180, and L is given 1.5. So calculating this, you will get the value of T, that will become 4569.26 Newton meter. Then power, we know that power is torque into omega, that is 4569.26 into omega is 500 by 60, that is rotation per second, and one rotation is 2 pi radian. And calculating this, you will get 239,240 watt. That is, it has been asked to find in kilowatt. So 239.24 kilowatt. So the answer is 239.24. So with this, we are ending our session here. We have solved all those problems of GATE 2023, which are from Applied Mechanics and Design. Thank you for watching this video, and please subscribe my channel to get more videos on mechanical engineering.